Thank you for joining today's WebGL WebGPU Meetup. We have an exciting line featuring WebGL updates from the chair of the WebGL Working Group, Ken Russell, GPU updates from Kelsey Gilbert, co-chair of the WebGPU Working Group at W3C. Following the updates, we will have presentations from Will Eastcott from PlayCanvas on 3D Gaussian splatting. Ivan Popelyshev from Tessera.io will demo bit mixing bone animations using WebGL2 shaders. And Stephanie Hurlburt and Reg Geldreich from Binomial will demonstrate working with HDR textures. But first, a couple of housekeeping items. If you have any questions during the presentation, please ask them using the Q&A feature located on your Zoom toolbar at the bottom of your screen. We are recording this webinar, and we'll share the link to the recording along with the slides on the event's webpage. At the end of the session, please complete the short survey to help us better design future events. With that, I hand it off to Ken Russell, chair of the WebGL Working Group. Ken?
So thanks, Jeff, and hi, everybody. Welcome to the Midsummer WebGL WebGPU Meetup. We're excited to have you here and to talk to you about what's new. So let's get started right now. Diving right into the updates. So a bunch of stuff on the WebGL side, some extensions and stuff, and then Kelsey will talk about a bunch of interesting WebGPU stuff. So diving right in, WebGL extensions. Yes, WebGL is still moving forward. A few extensions were promoted to community approved state since the last meetup. OES sample variables, OES shader multi-sample interpolation, and EXT render SNorm, letting you render to assign normalized textures. And this completes the set of smaller extensions that Alexei Knyazev proposed some months ago. And thanks especially to Alexei for driving these extensions. They're already shipping in Chrome, and they're coming in Safari 18. And by the way, the lower right link lets you get to these slides right now, and then you can click all of these links. So progress on Engels Metal backend. Work is still ongoing here, and this is already back in Chromium's WebGL implementation on Apple Silicon Macs and also all of Apple's implementations. We're ramping up shipments in Chrome on Intel CPU Macs. It's quite difficult to swap out the entire OpenGL implementation because the entire browser uses this for its own rendering. And so every little change or perturbation in performance characteristics shows up as a regression that has to be addressed. So it's taken quite some time. So in the interim, Alexei fixed a bunch of stuff in the backend related to parallel compilation and program linking. And this is already exposed as KHR parallel shader compile, that extension, but it's basically almost 100% working now on Mac with Engel Metal. We also fixed some bugs in flaky occlusion query results. And again, thanks to Alexei for many fixes in the Engel Metal backend. The full WebGL 201 conformance suite is passing on Engel's Metal backend. This is the first platform on which this vastly expanded conformance suite is actually passing 100%. And this paves the way for the next specification and test suite snapshot, which we're hoping to do in the coming few months. Kelsey Gilbert, our co-presenter from Mozilla, is driving a WebGL spec change, which is going to make applications more robust to WebGL context loss and restoration. Basically, when the context is lost, the browser is now going to return non-null objects from the creation functions like create buffer, create texture. And hopefully, this is going to make it easier for applications to deal correctly with context loss and restoration, avoiding null pointer exceptions that would otherwise potentially happen. So thank you, Kelsey, for proposing and driving this change and also revising the many associated conformance tests. We expect this to come to browsers within a couple of months as we finalize the specification change. And that's it for WebGL. Kelsey, would you like to take over for WebGPU?
Yeah, thanks, Ken. So this slide, I think, hasn't changed. WebGPU, as many of you are aware, is kind of the next successor to WebGL, if you will. It's not really replacing it. It's just providing the more like, metal D3D12 Falcon level of abstractions on top of hardware as we kind of move that ecosystem forward. The biggest thing people are always excited about is compute shaders, and low draw call overhead is like some of the biggest stuff. But of course, there's a bunch of stuff y'all are excited about that we're working on in the future. Development on that happens primarily on GitHub and at the W3C, and we'd love to have you participate. Next. Standardization updates, my bread and butter. So the current API and WebGL specifications are basically ready for our V1 snapshot. So that'll be when we actually kind of publish it, and it's a firm thing. Everyone is working on implementations to match where the spec currently is, but like the snapshot is when we say like this is the actual thing. So we're super excited for that. It's largely the cleanup phase right now. We're not quite there, but we're so close. We also still have steady progress on actual changes, not just cleanup. We've made a lot of progress on a compatibility mode for WebGPU, and the idea there is we have a bunch of hardware and devices that can't quite meet our requirements for WebGPU, like what we call core, the main API. But with some caveats, like that we share across a number of devices, we can bring WebGPU further back in time, back to like ES 3.1 level devices. So that kind of thing is really exciting, and there's been a lot of great work, predominantly out of Google on that one. And we're still adding things to the shading language. There's more things to add, but we have 8-bit dot products, primarily thanks to Intel's web graphics team in Shanghai. So thanks for that. And then more features are coming into there, but predominantly we're in the cleanup phase and solidifying things for our V1. Next. I got ahead of myself, right? Implementation status. In Safari, it's enabled in Safari Tech Preview, so please test it there. Firefox, enabled in nightly on Windows and Linux for testing experimentation. Mac is, I believe, coming extraordinarily soon. It's just not out yet, but we are planning to get a release out, or like have WebGPU ship out to release Firefox by end of year. Chromium is shipping on everything, basically everything. And then Chromium is also I believe, the most up to date with the top of tree WebGPU and WGL specifications. But implementations are mostly interoperable. Like the idea here is that we're in the please test it on multiple browsers stage. Please give us feedback. Please tell us what you'd like and what you don't like about it, because we're really firming this up to be the foundation for what we're starting to look at in the future. Next. 3JS, a lot of you are familiar with. They're getting they have a WebGPU backend. So as they're working on that, they've done a ton of awesome work, including on the 3JS shading language, to help paper over some of the pretty different shading language that you have in WebGPU versus WebGPU versus WebGL. So, but like when you use this, it kind of lets you just fall back from WebGPU to WebGL2. So this is like awesome, right? Like incremental progress here, and getting more activation for your users with these cool new features. Thanks to Sunag in particular for driving a lot of the re-architecture, and follow 3JS for the team's latest updates. Next slide. We have WebGPU samples. We brought these into the kind of the official like working group like zone almost. So we put them at webgpu.github.io/WebGPU samples. There's a bunch of cool stuff. Try them out. Submit yours. Like this is an open project. We're trying to get cool demos and show off what WebGPU is capable of. Next slide. There's a lot of partnerships. We mentioned 3JS, also Babylon.js working with. There's ongoing partnerships with a ton of teams. To mention a couple is Intel, TensorFlow, Google Meet, MediaPipe, and PlayCanvas has also been working on a WebGPU refactor. So keep an eye out for that. And we're also working with Unity to make sure that they're satisfied and can work with some of the new constraints we've in particular added to WGL around uniformity analysis. Next. And our big two favorite WebGPU resources are our tutorials. Well, tutorial WebGPU fundamentals is more of the tutorial. When WebGPU best practices is what it says on the tin. You might be familiar with WebGL best practices. If not, check that out. But WebGPU best practices is that, but for WebGPU, letting you know, like for a complicated API like this, like what some more hints and tricks and information on like what you should prioritize, and in particular the ways you should think about things. So please check those out. Next. Contributions. I mentioned this a little bit. Like we're so happy to have help, and we've gotten a ton of great help from the community, and we'd love to have more. You can help by just trying it out and giving us feedback. We'll tell you more about how to do that in a sec. Try publishing. If you're using a framework and the framework supports WebGPU, try it out. Try to conformance test on your particular machine. Us devs are trying it on our machines and our test hardware, but we want to make sure that it works on your machines too. So like if you run the test suite and it's not working for you, let us know. And again, like contribute samples and demos and articles using WebGPU. Like we build this together. So we're happy to have you help. Next. So here's the communities. The first up, I think, is the WebGL side. We have a WebGL dev list, which is an email list. And that one's particularly targeted at like talking with other devs and also us implementers. So if you want to know like what's up, or like have a particularly difficult question about how something's working, like please ask. Happy to have you ask there. We do have a Kronos's public WebGL mailing list also. That's more on the spec side of things than the dev side of things, but it's also public. And if that's useful, please use it. There's a WebGL matrix chat room for a more like live chat with us browser implementers and other developers. And there's also tags on Twitter, or the artist formerly known as Twitter, and Mastodon. Next. Next is the WebGPU side. We use the WebGPU. It's for historical reasons, it's GPU Web repository on GitHub. But that's where all the work happens. So if you have spec questions, things like that, that goes there. We have a WebGPU matrix chat room to talk again directly with us, but on the WebGPU side. And again, there's hashtags. And we look forward to hearing from you. Thank you.
Thank you, Kelsey. Next up, we'll have Will Eastcott from PlayCanvas, and he'll show us 3D Gaussian splatting. Will?
Thank you. Okay, so it's a pleasure to be back at the WebGL WebGPU Meetup. I think I first did this about 12 years ago. Anyway, my name's Will Eastcott. I'm the creator of PlayCanvas. I think I wrote the first line about 14 years ago. It's still going strong. Today, I'm going to be talking about getting started with 3D Gaussian splatting. And it's an interesting new technique that we have. Funnily enough, it was originally formulated back in the 1990s, but it's only since last summer when INRIA, a French research institute, released a paper and some accompanying tools and source code that this really started being used on modern hardware. But it's a way for you to be able to digitize the real world, capture it into a 3D scene. The first thing that I did when I started using this tech is, well, naturally, I scanned myself. And I was actually blown away by the quality that's achievable through Gaussian splatting. You can see the incredible like specular highlights picked out on my bike suit there. All of the different materials, the perspex on my helmet, the plastics. It's incredibly realistic. And the fact that you can generate this with simply using a smartphone and a computer in about 30 minutes is pretty mind-blowing. So let's talk about the workflow. So you can break the workflow down pretty much into three stages. There's a sort of scanning and generation phase. There's a cleanup phase where you need to essentially condition the data, and then you can import your Gaussian splat into your engine of choice and build an interactive application. So let's look at that stage one, scanning. It really works by taking photogrammetry data, so images, or you can use video and take frames from the video. And you feed those images into software that generates the Gaussian splat. Now, when INRIA published their paper, they published the tools that do this. But there's also other alternatives like Polycam and Luma that you can use. But essentially, what happens is it's a two-stage process where initially the original camera positions in 3D space that we use to take those photos, that's calculated. And then hundreds of thousands, if not millions of Gaussian splats, little blobs, are generated and fit to those images. And there's an iterative process that's run many thousands of times to fit those blobs as well as possible for each of the photos. And what's generated at the end is the model on the right there. Now, let's drill down a little bit into what an individual Gaussian is. So there you can see like the Gaussian is a volumetric particle. It's a blob. It has width, depth, and height. It has a color. It has an opacity. And as the camera is kind of moving around the scene, any of those values can change. So if we look at my original scan and just zoom in on the helmet there, and then we render the splats as little rings, you can see what's happening here. So there's a vast number of these splats, and they're being rendered back to front in camera depth order. So once you have your Gaussian splat scene, you'll want to process it, clean it up, and there's various reasons for that. When you're doing the training phase that I just talked about, sometimes you get stray Gaussians generated in that process. We call those floaters, and they're just hanging there in 3D space, and you want to just delete them. So with SuperSplat, you can load in your PLY file, select those stray splats, delete them. You also may want to just isolate a target object. So in this case, there's a bicycle. If we just wanted to capture that bicycle and delete the background, we can do that too. You can see at the bottom of the screen there, there's a histogram view. So you can also explore the data in terms of hue, opacity, position, scale, and so on. So it's a very powerful tool. But another key aspect or feature of it is its ability to compress splat data. So initially, PLY files contain floating point data. So the original position, orientation, scale, and color of each Gaussian is encoded into floating point numbers. So we've devised a compressed version of this data where essentially what we're doing really is just quantizing that floating point data down into integer numbers. And we're doing some other tricks as well where we're bucketing splats into groups. But essentially that's what we're doing. We're leveraging quantization. And also, you have in the original PLY file something called spherical harmonic bands that encode all of the sort of lighting, all the color data. And we just keep the dominant band 0, and we throw away the rest. And you lose surprisingly little data or I should say fidelity in the scene when you do that. So as a real world example, if we look at that original scan of myself, that was a 254 megabytes PLY file. But if I remove the background and I then further compress using the quantized format, the splat becomes only 8 megabytes, which is suddenly in the realms of a real-time web application. You could quite happily download that data. So it's pretty impressive savings. So once you have your compressed splat, it's all cleaned up, you're ready to build your application, you can head over to the PlayCanvas editor where you can just import your PLY files and any other assets that you have, and simply drop the PLY into the editor and get started. You can also create a photographic skybox to add even more realism. Just drop that into the 3D scene there. So you can see in the space of like a minute, you can just put together a very basic application where you can visualize and share 3D Gaussian splat on the web. Another really cool feature of the PlayCanvas editor is its ability to apply custom shaders and post effects to your scene. So splats are basically particle systems, right? They're made up of hundreds of thousands of particles. So you can write custom code that will animate the positions of these splats, or the color, or the opacity. You can apply a bloom effect or whatever you like, and you can come up with some really, really awesome transitions. And that's demonstrated by this, this statue visualizer app that I have here. Okay, so since we released SuperSplat and integrated Gaussian support, 3D Gaussian splatting support into both the engine and the editor, we've seen the community build some really, really impressive applications. And I'm hoping that some of these experiments will inspire people who are listening to this talk today to go out and get creative. So one thing that I'll just start off with is drone footage. There's vast amounts of drone footage that you can find on YouTube today. So here's an example of the Baltimore Bridge. So just download this video, run it through the tools, and out pops a 3D Gaussian splat, which now becomes interactive and explorable. And if you were, say, a news agency and you wanted to create engaging content very quickly and cheaply, this is a very compelling option. Also, we've seen developers start to incorporate Gaussian splatting into traditional mesh-based applications. So here you can see a game developer that has taken a splat of a vehicle and just integrated it with some vehicle physics and thrown it into a 3D world. And yeah, like super compelling. And again, I'd make the argument that it's awesome that a game developer doesn't have to go to a 3D artist to build this model. He can walk out onto the street, capture a vehicle sitting by the curbside, and build this sort of application very easily. Next up, 4D Gaussian splatting is another technique that's being worked on right now by folks. So essentially animating Gaussian splats over time. You can also see a 3D object, the PlayCanvas cube there, just plopped into the scene. So you can mix and match 3D geometry again with 4D Gaussian splats. But again, like it's very compelling that you can capture this kind of scene. Next up, earlier this year we saw OpenAI release Sora, and one of the showcase videos that they released was this gallery that was generated off the back of a simple text prompt. So the interesting thing for me is this gallery is a completely coherent 3D space. As the camera moves through the video, it maintains its dimensions. So again, like that makes it suitable for running through the tools, and I could just generate a Gaussian splat, drop it into the PlayCanvas editor, and add a first-person controller. So you can see where we're going with this. You can imagine we're getting to the point where we can hallucinate 3D environments with generative AI and then just create real-time applications with them. It's pretty exciting. So this is all within the first year of Gaussian splats being on the scene. I'm very excited about the future, and there's a bunch of work definitely that the PlayCanvas team wants to explore. We're looking at things, I've listed a few things here, like reducing the generation time. So if you're gonna convert photogrammetry to a PLY file, today it takes roughly 30 minutes. So we want to look at getting that right down. Also boosting the runtime performance of our engine. It's already heavily optimized, but with WebGPU, we're able to start exploring interesting techniques where we sort splats in compute shaders. So that's an area of research that we're going to be working on too. We're also very excited about the opportunities with animation. I showed you 4D GS on an earlier slide, but there's also opportunities to look at applying bone-based animation to Gaussian splats too. relighting or lighting Gaussian splats is also very interesting. The splats themselves encode the lighting as just colors. There's no data related to things like surface normals. So it's actually right now very difficult to relight a Gaussian splat. But I think this is going to be a solvable problem, and being able to add a Gaussian splat to any 3D scene, regardless of lighting conditions, will be very powerful. And lastly, just improving graphical fidelity is going to be important in the longer run. It's already pretty good, but when you start to zoom into a Gaussian splat, you notice the scene starts to break down, and you notice an element of blurriness. So that's something else we want to be working on too. So yeah, that's my talk for today. Thank you very much for listening. If you want to get started with PlayCanvas, with Super Splats, then head over to playcanvas.com. You'll find everything there, or over to our GitHub page if you want to get involved writing, contributing to any of the code bases that we have. So thank you very much for listening. If you want to reach out to me on X or LinkedIn with any questions, feel free to do so. Otherwise, over to the next speaker.
Thanks, Will. That was great. If you have any questions for Will, please use the Q&A feature located on your Zoom toolbar at the bottom of your screen, and we'll address all the questions at the end of the presentations. Up next, we have Ivan Popelyshev from Tessera.io. He will demo mixing bone animations using WebGL 2 shaders. Ivan, if you want to go ahead and take over the screen there.
I'm very glad to participate here, and I'm one of core contributors of Pixie.js, and I found a new animation algorithm for 3D models, and I'm gonna be boasting a bit, and if it will be too much, then Will Eastcott will bring me to Earth. Will, are you here?
I'm here.
Okay, so I will wait for, I will ask for your opinion a bit later. Okay, so what is the project itself? It looks like that. Many people know that look, it looks like other voxel sandbox games. I hope frames per second is enough for Zoom to show something, and I can spawn many mobs. So right now there are 300 calls. I can spawn 300 pigs. Please stop raining. Okay, and it works. And on my computer there are no lags. Game loop is like 23 milliseconds. It's fine for this count when I have 600 mobs, because I want that count of mobs to assault this village when the game will be ready. Okay, goodbye, because I need this performance to show other demos. Okay, so never happens that some algorithm, that easy algorithm was published like for something that was ready 10 years ago, and it never happened, and he will go again. Because previously I did something the same for lines for WebGL 1, but here we are working for WebGL 2. Okay, so basics. I think many of you people understand how to do the skinning. The skinning for models is done on GPU side. In the shader, you calculate the weighted sum of the bone matrices multiplied by vertex position. And to do that, you have to post, you have to upload the bones to the GPU. But on the JavaScript side and WebAssembly side, there is a very slow process to calculate those bone matrices. And what I want to do, I want to move this upload barrier to the left. I want to do more work on the GPU. And the main problem, I color-coded it in red. Color coding decision is also on screen. Okay, so the red, like a problem. The main problem is we have parent bones, because For every bone, we can calculate its local transform, but to make a modal transform, we have to multiply it by transform of the parent bone. And that is what difficult to move. So there is workaround that most engines in WebGL are using. For example, Babylon. Here we have 500. It might be 1,000 or 2,000 animations. It's called baked. Okay, it's called baked something, because baked, I hear from other people, baked vertex texture animations. But basically, all those matrices that we are calculating on the CPU, if we make discrete animations like 100 frames per second, we save those animations as matrices in the texture. We can save matrices, we can save vertices. It's different size and different performance for that. Okay, and that way, most of the work of the process CPU is done beforehand. It's very fast, but it has one big problem. There are basically no mixed animations. And what I call mixed animation, what everyone calls mixed animation, is where your character goes somewhere and the animation goes to his standpoint or to multiple. If I switch multiple animations like that, there are like 10 animations going at the same time, because I walk, then I stop walking, then I walk, but previous walk wasn't stopped. So I have to mix those keyframes together. And it's not possible with the baked versus approach. One thing that helps that our models are from Blockbench, and I have no bone weights, so only one bone per vertex. It's easier for me. Okay, so let's look at this left side of our of this thing, left side, and give it more details. The thing is, for every consider we have like 8 bones. Every bone depends on the previous one, like a very big pine of a tree, maybe. Okay, so for every bone we have original position rotation scale and animations with weights. There might be many animations. We have to make a summary of it, make a sum of all those 3 parameters, and then after that we have to make a matrix based on it, like matrix composition process, and we can do everything on the GPU. It looks like all the blue part can be done on GPU, but the red part can't be, because the number of those multiplications is different. We can't just use a previous result in the shader. If shader computed one bone, we can't use it to compute other bone because of WebGL limitations. So how do we solve it? Well, to multiply 8 matrices on the vertex is very bad. We have like 24 texture read for 8 bones, because each bone is a matrix. Matrix, it's 3 texture reads, and if there are whites, then it's completely bad word. Okay, so and on WebGPU we can actually do that, and that algorithm will cost us something about n multiplied by average of depth of our tree. But the thing is, what if we calculate it all on the fragment shader, like Excel table, like a spreadsheet? We have a texture with local bones, and we want to calculate it the model bones for it, all those multiplications. For it, for that we have extra space already. We can store the parent, the number of parent bone, and like we are doing filtering or post-processing, it's just possible on fragment shader, obviously. But that's not enough because, again, 24 texture reads, it's too much for us. And if there are more bones, if there is bigger depth, and if you have an artist, he doesn't understand coding, he just makes more bones, and everything. Anyone who used Spine or other bone editor knows how artists can completely screw your performance. Okay, so, but we can actually flip-flop that texture. The same way we are doing blur or any other post-process, we can do it through several iterations. We don't need like very big number of iterations, only the logarithm. Because if we originally we have link to the parent, but each time we have we swap the link of to the parent to the link of parent's parent. And that way we can, if we multiply two matrices on each step, after 3 steps, we already have everything for 8 bones. And the maximum depth in our current game models is about 13. So 4 iterations, and it can be done without a problem. So what are other advantages of this algorithm? First, of course it's worse than on CPU by just theoretically, but GPU has many cores, so that's why it's winning. The number of texture reads is actually very low, like 5 texture reads per 1 matrix row computation. The total number of reads also not that bad. Draw buffers isn't needed, because if you want to calculate whole matrix in the one fragment shader, you need draw buffers, because you have to write several pixels, like 3 matrix rows. But it's not needed. You can just calculate each row independently. The other thing is we can store position, rotation, scale, and upload it to GPU every frame, and GPU will calculate our matrix in the same shader. It's just obvious it can be done, and I already do it. It also gives extra performance. If you have a batching for your meshes, you can just store the relative parent index, and it will be much easier to assemble the array of all the matrices. I will show it later. Okay, so, and if there are pure CPU calculated matrices, like where you need inverse kinematics, then it also can be done. You just write them in the end, and they don't participate in this flip-flop process. So the shader itself, I divided it by 2 slides. So it's easy. We just read original matrix, read 1 row of its parent matrix and multiply them. And maybe we look for relative parent. If parent index is relative, we have to calculate which matrix it actually is. That is all of the shader. So what did I do? I just pushed this barrier of uploading to the left, and it can be pushed even further, because we only need this orange values. We need a number of animations and whites. Yes, we can have like 10 animations affecting the same bone, but we can flip-flop that process too. So it's not a problem to move this thing that way, this barrier, so it will upload only those orange values, and everything else will be done on the GPU. Okay, so Will, can you tell me, please, what do you think about it?
Well,
and whether PlayCanvas has it?
Yeah, it's very cool. The PlayCanvas engine, the blue line is kind of where it's like it's just to the right there. So we just upload a skin matrix palette, and we don't consider any of the animation data on the GPU. So this is a very interesting technique, and PlayCanvas's graphics engine, is completely separate to the animation system. So, there'd have to be a deeper integration there, but it's a very cool technique. Nice job.
Thank you, Bill. Okay, so and I have pair of bonus slides. I hope I have time for it. So the bonus slide, because of compute shaders, I have to port my game also on WebGPU because I really need compute shaders. If compute shaders were on WebGL, then I wouldn't need it. But here we go. So I have a number of complaints and good things to say about WebGPU. First thing is bit shift is evil, because this is the only place that requires our unsigned integers. And I am a Java guy, and unsigned integers don't exist in Java for a reason, because it's very the code becomes very bad because of it. So that's the biggest complaint about it. So easier complaint, clamp minimum and maximum do not allow the usual trick that is used in all shader toys. This can be fixed, obviously. It will be very cool if it fixed. The problem is there are no defines and no unused function, special function calls. That means the concatenation of shader lib, how 3JS did it for the WebGL and how other guys did it for their own engines. I know about it. Like concatenation is it's super hard. Like, so instead of concatenation, we have to use our own TypeScript-based shader language. It reminds of what 3JS did, but it's not node-based. It's just like GLSL or WGSL, but like we have imports like TypeScript. We can share structures and constants, and this language is not published yet, but it's working. I already my game shaders are already working on WebGPU. So relatively easy instance divisor and no intersecting instances. Okay, we can live with that because storage buffers. Derivatives are very well done because people don't know how they worked, but now it's more obvious. Thank you. And the best thing about WebGPU is the limits, because now if I hit the limit, I will know it on my computer, not on some guy's device that I will ask the guy to please bring me the report from your device with all limitations. No, I will know it on my device. I will be informed about it. I will raise the limit to the maximum of this of device reported to me if I need it. But this is the bad thing about WebGPU. And I have a second bonus. Shout out to guys from AMD, because Radeon JBO profiler works on WebGL 2 and gives a lot of information. You just have to enable Angle DirectX 12. It's just awesome. I see assembler. I optimized that assembler for integrated video cards of AMD. It's just perfect. Okay, that's it. Thank you.
Thanks, Ivan. That was awesome. If you have any questions for Ivan, please use the Q&A feature at the bottom of your toolbar there, and we'll get them answered at the end of the session. Right after the next presentation from the co-founders of Binomial, Stephanie Hurlburt and Rich Geldreich, they will demonstrate HDR textures. Stephanie, if you want to go ahead and take over the screen.
I am so excited to be here. This project has, in some senses, been many years in the making, but we've really been drilling down on it for the past year. HDR on the web, GPU optimized in a cross-platform way. It's really, really cool stuff, and it's exciting that we get to announce it here and at SIGGRAPH. So HDR is not widely used depending on the application you use, but it is becoming more and more common. So basically our screens don't look realistic in a number of ways, but one of the key ways is just the range of light that you can see. When you go outside, you're blinded by the sun. It takes your eyes a moment to adjust to dark spaces. When you're watching your computer screen, it's just your computer screen. And HDR hardware is becoming more common, and that's very exciting because that's going to actually physically increase the brightness and the darkness of various aspects of the screen. But also, you can use HDR technology even in SDR screens. And one of my favorite examples is just photography. That's a big hobby of mine. And I can take a picture in HDR of a really bright window in a really dark room and then edit it in post so that you can see out the window, but you can also see in the room. And it kind of mimics the way reality feels when you're actually looking at it. And you can do similar things. There's a lot of lighting pipelines that make great use of HDR to optimize their pipelines and to make it more realistic. It's really cool. What we do is we do image and texture compression. So what we do is with our SDR work, with things like JPEG, it's uncompressed on the GPU. With pretty much all graphics, image compression tech, it's uncompressed data on the GPU, and it might be really compressed and really optimized on the CPU side, but once you shove it at the GPU, you're just dealing with pixels, and we can do better than that. What we do is we do GPU compressed textures. So we take advantage of GPU hardware that keeps the texture compressed in the GPU, so you can massively boost performance. And with our SDR codec, we're the same size as JPEG on the CPU. So it's kind of a win-win. And there's a transcoding step in the middle, which I'll talk to you a bit, that's real time and takes about the same time as decompressing JPEG anyway. So it's so great to be able to take advantage of GPU hardware. And in some applications like VR, games, maps, you literally need to. Like before RTech came out, some of those applications were just storing GPU textures, like bucketfuls of storage on the CPU, and we allow you to actually have good storage size. So this is the pipeline for our SDR codec. We actually transcode to more formats than this, but I didn't want to stuff up the screen. You take the source image, you encode it with our encoder, Basis Universal. You go to KTX2, container format, and then in real time, you transcode to the GPU compressed format that GPU needs. In HDR, it's really similar. So for mobile HDR, ASTC is the GPU compressed format, and desktop is BC6H. We recognize that some people want to take advantage of our good storage size, but they do want to work with HDR uncompressed when it comes to actually working on the GPU. So with HDR, we also offer that option and have float. So you can really do it case by case, and you can kind of decide for your pipeline which is best in which different use cases. For source images, we work with EXR, .HDR, and PNG. We can also work with others in the future. So with this release, we are giving you 6x compression in storage size, which is huge for HDR especially. But with GPU, you also get 6x compression, which is really, really cool. Our work is open source. We're going to be releasing end of August, early September. And so you'll be able to check it out. It will be on the Basis Universal repo. We'll have one format that will work across different HDR implementations on various GPUs. The format for this one is just a simple subset of ASTC. So there's actually no transcoding time for mobile devices and a little bit real time for desktop. And it's just awesome. We're going to work on WASM transcoders to come out with the release, so you'll be able to use it on web. And the quality is really high. You'll see in the example images, it's basically the highest we can go. We had to zoom into the pixel level for this presentation, because even then you can't really see a difference between ASTC and ours, but it's really cool. So that's kind of the overview. I hope for those of you who weren't familiar with HDR or aren't familiar with what we do, you kind of get an idea of what this is like. For those of you who are already familiar, I wanted to include a deep dive into what we do as well. And Rich will take care of that.
Thanks, Stephanie. Really appreciate it. And I'd like to thank everyone for inviting us here. So yeah, when we started this project late last year, we weren't really sure if this was doable or not at the transcode speeds that I think we would need for web. And so these slides I'm sorry, they're very detailed. So I only have a few minutes, so I'll go through them pretty quickly. So here's how this tech works, that we have a reference encoder, which encodes to a standardized subset of ASTC HDR. We are taking this massive complex format, ASTC, it's the most complex GPU texture format, and simplifying it so that it can be efficiently transcoded to the desktop HDR form, which is BC6H. And so ASTC was developed by amazingly visionary engineers at ARM and AMD quite a few years ago. ASTC supports LDR and HDR for tons of different block sizes, lots of different configurations, upsampling for the weight grids, like a ton of features in there. It's legendarily complex form. Unfortunately, ASTC is not supported on desktop. At least Intel actually did release a few CPUs to support it, but last I heard, Intel's dropped support for ASTC. So on desktop and some consoles, the good enough format is BC6H. These are both 8 bits per texel formats. So right now, what developers do to distribute HDR texture content is they either offline encode twice to ASTC and BC6H using 2 different encoders from 2 different sources, or what they do is they real-time encode on the target. And so we have a third option that's coming. And so what we do is we encode to a common subset of features and capabilities between ASTC, HDR, and BC6H. So we're calling this UASTC, where U means universal. We've already shipped an LDR variant of this. This is our HDR variant. And believe it or not, this is actually simpler than the LDR variant because it's just less a target GPU formats to worry about. In our case, it's just ASTC and BC6H and just uncompressed. So what we're going to do is, with our reference encoder, we encode to ASTC. It's 100% standard ASTC data. However, it's going to follow a specification we're going to release by the end of August or early September. And this specification indicates which very strong subset of ASTC encoders are allowed to use. If an encoder uses that subset, then our transcoder will be able to take that data and automatically convert that to the BC6H block configuration. So we're not recompressing pixels. We're not decompressing the entire ASTC block of 4x4 texels and then recompressing that from scratch. Instead, we are just converting ASTC's block configuration directly to BC6H's block configuration. So the deal is, we don't assume that the target platform has SIMD. Without SIMD, you're just stuck basically with scalar operations, and that really does limit you what you can do. So if you've ever written any kind of GPU texture encoder that supports like BC7 or supports multiple partition patterns, it's actually a quite expensive search. Our stuff doesn't need to do that search for BC6H. Of course, the trade-off is when we go from ASTC to BC6H, that can be lossy. However, and I'm actually really surprised by this, the error is only within a fraction of a dB PSNR. Okay, so I'm just being upfront in these slides. There are pros and cons. It's all about trade-offs. So the pros, it's just constrained to ASTC, so we can leverage the existing ASTC spec from Kronos, all the existing tooling, infrastructure, knowledge, etc. It's simpler than ASTC, the full format, so that it's relatively easy to write an initial encoder for. The advantage to this is there's no transcoding whatsoever on ASTC GPUs. It's just either a mem copy, or you just give the driver the API a pointer, and that's it, because it's just standard ASTC. Existing encoders can be modified to support this subset, and I think that actually be fairly easy to do. And the encoder can be improved over time without changing the spec. And so the cons, to be completely upfront, is that because we're not utilizing the entire format, there will be lower quality than max achievable. And I'm going to have some graphs in a second about that. And so because we are a union of both BC6H and ASTC, there's 2 things that we don't support. Currently, we don't support alpha. I actually think we could get alpha in there. And then so ASTC HDR does support alpha. BC6H does not. Currently, we're just the subset. So we're just, what's in common between them both. We also do not support negative values because ASTC does not support negative values. But however, we do support all positive non-nan, non-infinity half float values. So this is a full HDR codec. And of course, like ARM has had, that ARM released ASTC Enc. It's an open source repo on GitHub. It's the best ASTC encoder around. But they've had like approximately a decade to work on that. We're releasing a reference encoder, so it's not going to be as fast, but we can make it faster. So in terms of risks, so because we're going through a standardization process, I just want to be upfront about the risks here. Is that in our world, we analyze millions and millions of different blocks to see what the quality is like in ASTC and BC6H, and there's always a possibility that there are outlier blocks that encode well to our subset of ASTC, but could have excessive artifacts in BC6H. And so that's what we've been intensely working on, is to make sure that these outlier blocks are either as few as possible or there aren't any. So once we have a spec, and this is up in the air, I think the spec, it's fairly easy to define the subset, because we're just going to refer to Kronos's ASTC spec and then say, okay, you can only use X, Y, Z, and W, and you can't use these other things. That's easy. However, do we spec the transcoding algorithm? And there's some pros and cons to that. So I think what we're going to do is suggest an algorithm, and then that would allow developers to improve the transcoder over time. Okay, and the other risk with this is that it's possible that the subset that we've chosen might not be strong enough for everyone. I kind of doubt this. The quality is actually pretty high. Okay, and so real fast, these are the features that we're going to support. For sure, we're supporting solid color void extent blocks. These are nitty-gritty ASTC features. It's a very large specification, and so we're just distilling it down to these. We're supporting ASTC Keller endpoint mode 7 and 11, 1 or 2 partitions. We're also supporting a bunch of different texel weights. These are per texel weight ranges here, from 3 levels to 16 levels. We're supporting 2 partitions. However, we're only able to support 27 partition patterns, the ones that are in common between BC6H and ASTC. That's, in practice, not really the big constraint, because BC6H only supports 32 total. The weight grid must be 4x4, so we're not going to support weight grid upsampling, although we've experimented with it, and we could. Anything else in ASTC is not UASTC HDR. So notably, we're not supporting dual plane or any other SEMs. The only other SEMs I think that could be useful would be the luminance SEMs, but the quality gain, it's hard to justify for the increased complexity. Okay, so here's the transcoder. So what the transcoder does is it unpacks the physical ASTC block to configuration, and then it goes and chooses the BC6H mode which best matches it, and that also corresponds to the number of weight bits there. And so yeah, anyway, I'm gonna, because I have limited time, I won't get into too many details there, but there's the slide if you want to look at it offline. So anyway, what I'm going to get to next is some images just to show you, and some graphs as well. Okay, so here's some quality graphs. What we did is we chose a bunch of fairly well-known true high dynamic range photos, and we encoded them with ARM's ASTC Enc with its thorough setting. So this is the highest quality ARM's encoder is capable of. It's the highest quality ASTC is probably going to get, more or less. And then we also encode these images with our encoder, and we also transcode from ASTC HDR to BC6H using our transcoder, and that's in green. And so you can see ARM's encoder is in blue, and higher is better quality. And this is a FP16 PSNR DB. So we actually are computing our quality metric in half float space. And you can see across this that we are, as expected, lower quality. However, we're not losing much quality here. It's only a few dB, and on some harder images, it's like 10 dB, but we're already above, 45 dB or so. We're in BC7, BC6H quality, ASTC HDR quality range here. Visually speaking, I'm gonna go to some images now, and so I want to emphasize that, of course, we're looking at LDR tone mapped versions of the HDR image. And so we've used a very standard, very vanilla tone mapper called the Reinhardt tone mapper. It's well known. It's been around for a while. On the left, there's there's a very zoomed in version of the source image. And then in the middle is our UASTC HDR, which is a subset of ASTC HDR. And on the right is our transcoded version. And if you look close, you can see a few blocks where it's noticeably different. However, subjectively speaking, it's very, very hard to see differences with this encoding. So I'm going to go to some other examples. Here's another one, desk. Again, with the same tone mapper, so we can visualize this in slides reliably. Left is the source, middle is our ASTC HDR subset, and then right is the tone map. I'm sorry, right is the BC6H transcode. Anyway, it's actually really hard to see and visual differences here. There are some in some blocks, but subjectively speaking, it looks really good. And now I'm going to go to another one where it's a little more zoomed out. This is tree. This is the source image, Reinhardt tone map. So that's the source, your uncompressed data, half float. And then this is our compressed version, ASTC. What I'm going to do, I'm going to go back to the source. This is ASTC HDR compressed. You see, it's very hard to tell a difference. There are differences though, but it's a lossy codec. That's to be expected. Now I'm going to go to the BC6H transcode. And so what I'm doing now, I'm flipping between UASTC HDR and the BC6H transcode. And for all practical purposes, they're virtually the same. And so anyway, that's I'm sorry I couldn't get into some other more detailed slides, but I just wanted to keep it down around 10 minutes or so. Thank you very much.
Yeah, and so all our slides will be shared if you want to kind of know details, but our hope is that more people, especially on the web, use HDR. And with our technology, you can hit GPU acceleration on mobile and desktop, and even uncompressed if you want to work with that too. And you get 6 times savings on both the CPU and the GPU, which is virtually unheard of right now. So if you have a really GPU constrained project, I hope this helps you. And there's no question that's stupid. Feel free to ask us anything. We are happy to share what we know.
Yeah, I just want to throw in one last thing, is that this tech also works with LDR images. So we accept .exr and .hdr as the source file, but we also accept .png as well.
Yes, and you can find our open source repo that has the SCR work at on GitHub. And we're also actively standardizing this right now. So we welcome feedback. And I think that's all. But thank you so much, everybody.
Thank you, Steph and Rich. That's awesome. And just so everyone knows, we will have all the slides available on our event webpage for this webinar web meetup. So that will be available to you by the end of the week. And so if I could have all the speakers turn on their cameras, what we're going to do now is we're going to have the Q&A session, and I will have Ken go ahead and take over. Ken?
Super. First, thank you all the presenters. This is just awesome technology, awesome projects, and really thank you for joining and presenting this stuff. Now to the audience here, please use the Q&A function at the bottom of the screen or in your Zoom application. Just type in anything that's on your mind. We're here, happy to talk, and that's really the point of this, to be an interactive session. So jumping right into the first question here. Emil asks, I guess, Will, what are the advantages of keeping the splat rather than meshifying it?
Well, its visual quality is quite different after meshifying a splat, because splats are actually very good at representing like fluffy or furry surfaces, for example, or hair. And if you meshify those, you lose that. And the other thing is, when you probably saw in my bike seat, as I was as the camera was moving around me, the Gaussians encode the specular highlights. It's just color that changes based on angle, but it works really, really well. And again, unless you can somehow, as part of a meshification process, generate PBR textures, I mean, you're not going to get something that looks as good. So I think quality is a big part of that. But to be honest with you, it depends on the application and the object that you're scanning. Some objects might work quite well as meshes, but certainly certain types of objects are very well suited to splats.
All right, super, awesome answer. Emil, if you had any follow-ups, please type another question in the Q&A. And Will, I love your scan of yourself in the bike suit. All right, so Neil Trevitt, who, by the way, everybody, is the Kronos Group president and also a client, asks, nice work. Is there a desire or opportunity to formally standardize the super splat compressed format, maybe include it in GLTF? Will?
Yeah, great question. We would like to see more tools and engines adopt the format. I think standardization is a good thing. Yeah, I think that will happen over time. I mean, a lot of folks are using Supersplat to target lots of different engines. Yeah, like I think it's gonna be a short while before everybody understands the huge benefits from leveraging this compressed format. But yeah, it's something that I'm going to try and drive. But at the moment, I think it's just the PlayCanvas engine that supports it.
Okay, all good. Incubation in your own engine sounds great. And maybe once we gain a little collective experience in the industry, it would be a good time to sediment it. Okay, so the next question is also for Will. The anonymous attendee asks that in the text-to-video demo, the museum one, the quality of the wall and textures kind of changed as the camera moved around. And the question is that a level of detail process? And if so, do all the Gaussian splats come with LOD information, or is that generated by PlayCanvas at some step in the process?
Yeah, okay, great question. So the thing about the video is that essentially it played back as if the camera was dollying down the length of the room. So what I kind of found with the splat that was generated was that it kind of only looked reasonable from like a very limited field of view. And if you rotated the camera, the scene would completely disintegrate. So if I had used Sora, I would have said something like, do a camera track that like rotates around on a point or like moves around the gallery 360 degrees. And then I would have got like an environment which the splat generation training process could have like done a decent job with. But yeah, based on that particular video, and it's the only one I had because I couldn't access Sora, like that was the kind of the best I could do. But it was to give you a flavor of where we're going with this sort of text to video and then video to splat thing. And the fact that like as content creators, it's going to become like trivial to build like really amazing, Gen AI generated immersive environments. So that's kind of on the horizon.
All right, that's super cool. With PlayCanvas's engine being open source and your Gaussian splat implementation being in there, maybe the next version of these LLMs is going to crawl your source code, understand how to generate splats a priori, and it'll just generate the splats for you.
No doubt.
Right. Okay, the next anonymous attendee asks for Ivan. What is the advantage of doing the compute on the GPU versus on the CPU like PlayCanvas? You probably already answered this. Is it about making the animation dynamic, like making it respond better to actions in the game so nothing's baked? Oh, I think the question just disappeared out from under me. But Ivan, please feel free to answer. And you're muted if you're speaking.
Okay, sorry. So what is the advantage of doing the compute on GPU versus all the CPU like PlayCanvas? Is it about making animation dynamic, like making it respond to actions in the game, so everything is no longer backed? So the advantage is you don't have to degrade your animations by using baked animations on big number of entities. Because you can usually people do it like degradation, like near you is good entities that are very with the quality, and the farther is entities that are deviate. So in my case, after all of optimizations, because there are many steps I just couldn't put in the time frame of this presentation, but using this approach, it's possible to make many steps, to make like five times increase of entities. And moving matrices alone, this step was about 20% for me. On the empty map, like just empty map and mobs, nothing else, just pure. So there is, of course, architectural trade-off. Like the code has to be made a bit better. You have make better batching algorithms. But the thing is, with this approach, also if you compute something on CPU like inverse kinematics or something like that, sum of vertices or something, it still you can do extra upload in the same textures or buffers, and that way you will use both GPU accelerated stuff and the regular CPU in case you need custom logic. And this is a better approach than if you just do a game from scratch using only compute shaders. Like some people are doing, like Noita, like some other voxel games. They are making it. It's completely fine. But if you want to move your game from CPU to GPU, my approach is smoother. Okay.
All right, cool. Good detailed answer. Thank you, Ivan. And please, others, feel free to follow up with more questions. So the next question from Teo, longtime WebGL Meetup attendee, saying to Stephanie and Rich, interesting talk about improving image quality. So please show us some images. You did show us some images. I think the question came in before you did. Do you have any others that you would be comfortable putting up on the screen?
No, I do. I constantly look at images all the time. I only prepared a few minutes of slides. Yeah, the reality is this, is that if I showed you the compressed image, you wouldn't see any difference.
You literally wouldn't. That's why we had to zoom in to the pixel level.
We can't actually, to be honest with you, while developing the codec, we can't look at the images and make progress. We have to look at statistics. That's how high quality it is. However, with outlier blocks, if you zoom in really far, you can see the difference. But if you ever used a BC7 or a BC6H, yeah, when you compress, it's very hard to see the difference.
So in terms of quality benchmarks, it basically is no different.
Here's the problem too.
But in terms of HDR applications, you can research all kinds of amazing things that people do in HDR. Keep in mind, you're probably doing it on an SDR display, but you can at least look at various tone mappings to kind of get an idea of the range.
Here's the other problem. If I showed you an image right now, it would be compressed with zoom. And so what are you looking at? Are you looking at zoom compression artifacts, or you're looking at our compression artifacts? That's why in my slides I zoomed in.
But I really encourage you to dive into the world of HDR and see all these amazing things that you could do with it. It's really cool.
All right, awesome answer, and super relieved to hear that actually the quality differences are so imperceptible that you have to zoom in like 10x or whatever in order to see them. That's really, really encouraging from the standpoint of a cross-platform codec. So Teo put the link to Basis Universal in here, which I think I will dismiss. Thanks, Teo. All right, so Mohammed Reza asks, hi, I'm Fedora packager working with AI SIG, and I was wondering if SuperSplat, so a question for Will, supports other hardware acceleration other than WebGPU, such as Vulkan.
So SuperSplat is a web application, and the PlayCanvas team is all in on web technologies. Everything that we build is designed for the browser. So yeah, it's as a tool, it just runs in the browser and harnesses WebGL. We'll probably update it to WebGPU in the near future. And but like obviously the PLY files it outputs, you run those in whatever engine you like using whatever backend you like. So it's just a tool for editing, conditioning, optimizing Splat data. That's it. How you use that Splat data after it's done in SuperSplat, that's entirely up to you.
Okay, sounds great. So Mohammed Reza, you just got to include at least one web browser in your distribution, and then you can run the SuperSplat tool on your Linux distro. Okay, let's see. Just to rotate around here, Teo says nice to Stephanie and Rich, so very good. Let's see, so Clayton Bennett is asking for Will again. It seems that with PLY with your compression is the best way to compress a point cloud. His work is mostly on local with the FBX SDK, and he wants to leave behind that for smaller files like GLB and web-based modeling like Babylon.js. So you've made him curious about PLY, and would you say that compressed PLY can be good for web as well as local? Because it sounds like rendering time is the major choke point.
Well, when I say web, it's just that, I'm mainly concerned about people building web applications based on Gaussian splatting. So in those instances, download size and time is pretty critical because, You don't want your users to bounce while they're trying to access your application. Yeah, PLY is just something we use for Gaussian splat data. Everything else in PlayCanvas relies on GLTF. Neil mentioned somehow leveraging the compressed format that we have in the GLTF spec somehow, or creating an extension. I mean, I haven't really thought about it too much. I haven't really thought about how Gaussian splatting might be integrated into GLTF. Yeah, I think that's something I'm going to have to chew over, I think. Yeah.
All right, all good. A lot of cross-pollination here. I'm going to move around a bit. There were some questions asked on a doc earlier. So to round robin this question to Ivan, will you open source your TypeScript shader language?
Yeah, it's a prepared question. So as I think we made it for the game, and not all who made this thing are pro open source. So it's under question. However, I will certainly use it for Pixie.js plugins to move all the plugins from V7 to V8 Pixie, and help with Pixie.js, because honestly, Pixie.js high shader approach for WebGL and WebGPU is very strange. So, and if I remake this language and make it for public, then it probably will have plugin system, so you can easily put whatever primitives you need for WebGL and WebGPU into the language your own way, because all those differences and all those new functions in WebGPU and WebGL, it's not possible for one or several people to code everything. We have to make a plugin system that if person understands how it works in WebGPU and WebGL, then he writes his own implementation, and it's better, and it will be better. So it's possible for it will be possible for public use. I think someone in autumn, but it needs a rewrite. Okay.
All right, sounds good. Let's see, moving on to the next question. So Don McCurdy, major contributor to GLTF, asks for Stephanie and Rich, what's the expected transmission size over the network for UA-STC HDR compared to compressed EXR? Does UA-STC HDR benefit from KTX2 super compression methods like ZSTD?
Yeah, so yes, the answer to the second question is yes, it can and does. We're not right now focusing on getting the transmission file size as small as possible, although we have put a bunch of research into it. So right now, UA-STC HDR, which is UA-STC HDR is a subset of that, is 8 bits per pixel or texel. With Z standard compression, I'm just in general, it's like 7.5. It might, if for a simpler texture, it might be smaller. EXR is an interesting question. EXR is a vast standard, and depending on the library you use, either you can read an EXR file or not. So EXR is not really a universally interchangeable file format in my experience. With that being said, it's hard to say. There's a bunch of lesser used lossy and lossless EXR compression modes, but the problem is because it's not interchangeable to all the different libraries, it's really hard to say. So anyway, the thing is, EXR has to deal with at least 48 bits per texel, and you can zip that up. What are you going to get out of that? I doubt you're going to get much. So we're already down to 8, 7.5, 8, something like that right now. By the way, we're working on the next version beyond UA-STC HDR, which will have built-in compression. And I think it's very possible to get it down to around 3 or 4 bits per texel.
But 8 bits per texel is already a significant reduction in terms of
6:1.
transmission. And we wanted to make sure, especially for HDR, that folks got the best quality first. So we're happy that we're able to reduce size by that much with the quality that we get.
Yeah, and one last thing is that to answer the first question we got, what we do for testing is we have a 1,000 nits monitor. I send the slides. We do test with that a lot, HDR monitor, and we also use various viewers which have an exposure control. So we do, these are real HDR images. Unfortunately, because of this, because of Zoom, it wasn't clear how I can actually show it. So that's why I just showed Zoom and stuff.
Yep.
All right, this is super. Yeah, I mean, a 6x, file size compression off the bat, and that same compression on the GPU is really tremendous. So I just want to underscore that. Right. Super exciting. Oh, wow. More questions coming in. All right, let's get right to them. So G. Lu asks to Ivan, can we get the maximum GPU memory we can use for WebGPU in the browser to avoid crashes? In WebGL, it's difficult to find this limitation.
Okay, this is this is hardest limitation of everything I met in my experience. So regarding WebGPU, whatever you find on WebGPU report.org, any limit it shows, that limit you can override. Right. So I don't see a limit on the GPU memory, and I know that GPU memory is a very, very strange, how it measures, and whether actually resource still on CPU or on GPU right now. So it's more a question for Ken and Kelsey whether that thing is possible, because if it's possible and it will be made, that so many people will thank you. It's a bigger, very big question. So Ken and Kelsey, what about it? Is it even possible?
So we brought the question to Kronos years ago, asking for a standardized way to query like available GPU memory, and unfortunately, the OpenGL working group said that it was infeasible. The different GPU architectures have too many slightly different limitations on, like, okay, this memory can only be used for textures, and this memory can be used for buffer data, but only if bound in a certain way. And basically, there's no standard way to query it. So we basically did not pursue that avenue in WebGL. Nowadays, I think we may as well just live with the limitations of the WebGL API as they are and focus more on WebGPU and like the maximum buffer size that you can actually query and expect to get an instance of. But Kelsey, do you have more thoughts?
I think those are the main ones. It's just like Ivan said, especially like it's a hard thing to measure. We'd love to be able to tell more about like the shape of the system and like what the limits are, but we have to like figure out how to do that first. So it's something that like I think it'd be a good thing to talk about in to bring it up with the standardization bodies. So like bring issues up with the WebGPU and WebGL groups, and like maybe we can take another look at it, but I don't think I have any easy yeses for you, unfortunately.
Yeah. So the next question from another anonymous attendee is probably for Kelsey on the WebGPU side. When can we approximately expect the following features to be supported in shipping in WebGPU? 1, mesh shaders. 2, bindless. And 3, 64-bit integer atomics.
Yeah, I can't give you dates. I know you'd love to have like a rough approximation. We're hoping to be able to talk about those more in standardization later this year. Right now we're focusing on getting the main spec out the door. When are those going to show up? I think we're going to start talking about them late this year, and then maybe be actually doing more spec work on them next year. So they're a little bit in the future. We definitely want to do like bindless is one of the things we are very interested in picking up, but we really do need like a stable foundation before we jump into how to do bindless. 64-bit integer atomics is probably the one that like is probably the lowest hanging fruit of those. That one I totally could see it starting to show up. Basically, as soon as people have enough interest to propose features for it, and we have time to look at it, the same way that we've added support for like 8-bit integer, like dot product stuff, built-ins. So definitely things that you should like reach out to the like check in on the WebGPU like GitHub community board and like the issues there, and see. Like, search for them there. If you don't find something, ask about it there.
Yeah, sounds really good. Okay, well, with that, the Q&A queue is drained, and I wonder whether actually we should consider wrapping up. What do you think, Jeff?
I think so, Ken. Thank you. And thank you to all the speakers today for the wonderful presentations. We truly appreciate your time and effort in putting them together. As a reminder, a recording of this presentation along with the slides will be available on the Cronus Group website, and a direct link will be sent to you in a follow-up email. As you leave the webinar, please take a moment to fill out the survey that pops up. Your feedback is important to us, and it helps us improve the presentations. And please let us know if there are other Cronus-related topics you may be interested in. And thank you for joining us, and have a great day.